Hello everybody, Math Hobo here, and today we are going to be finding the solution to the b sub n coefficient of the Fourier series. So let's recall the Fourier series is defined as f of x is equal to the Fourier series, which is an approximation using trigonometric functions, or a sum of trigonometric functions, is equal to sigma n equals 1 to infinity of a sub n, is equal to a sub 0 plus sigma n equals 1 to infinity a sub n cosine nx plus b sub n times sine nx. And so far we've determined a sub 0 and a sub n. A sub 0 was for a function that is periodic over 2 pi. A sub 0 is equal to 1 over pi times integral from 0 to 2 pi of f of x dx, and a sub n was equal to, this should be 1 over 2 pi, and a sub n is equal to 1 over pi integral from 0 to 2 pi of f of, that's a bad f of x times cosine nx dx. So we've determined the a0 and the an. Now what's left is to determine the bn. And, well, you might say, okay, well, what is b0? So b0 will not be included in our solution. So we can just begin by saying our solution to bn is valid for all integer n greater than 1, and b0 will be defined as 0. And this colon equal sign just means defined. So it reads b0 is defined as 0. So let's begin. So we would like to isolate this bn term and determine the weight on varying frequencies, varying functions which have varying sine functions with different frequencies. So let's begin by multiplying both sides of this Fourier series equation by sine of kx. And in the previous derivation, in the derivation of a sub n, we multiplied by cosine kx. So here we'll be multiplying by sine kx, because it yields some very nice workable properties. So then we have f of x sine kx is equal to a sub 0 sine kx. Actually, you know what? What will be faster is if we can squeeze 2 steps into 1. So at the same time, we'll multiply by sine kx on both sides, and we will take integrals on both sides. So then we have the integral from 0 to 2 pi, integrals from 0 to 2 pi on both sides. Integral from 0 to 2 pi, since it's periodic over 2 pi, of f of x sine kx is equal to the integral from 0 to 2 pi, a0 times the integral from 0 to 2 pi of sine kx, and that plus the sum, the infinite sum, from n equals 1 to infinity of a sub n times integral 0 to 2 pi of cosine nx times sine kx and dx squeezed in there. And then all that plus, and then if you notice what I'm doing here is I'm factoring out the an, and I'm taking the sum outside of the integral, which is valid, and then I'm leaving the cosine nx times the sine kx, and I'm integrating that part. So I'll do the same thing for the b sub n sine nx part. So then we have plus infinite sum n equals 1 to infinity of b sub n integral 0 to 2 pi of sine nx sine kx. And now, you might be wondering, well, what is k? K we define to be an arbitrary positive integer. So, or just an arbitrary integer. So k in integers. So let's remember this. And now let's attempt to simplify this equation, which contains quite a few integrals and quite a few sums and looks quite gnarly. So let's begin with the first term on the right hand side, which is a0 integral from 0 to 2 pi of sine of kx, and there should be a dx there and a dx here as well. Forgetting my infinitesimals. So yes, this integral will evaluate to 0, because the integral from 0 to 2 pi of sine times any integer coefficient times x dx is always going to equal 0, and we've discussed this in a previous video in the Fourier Series playlist. So this entire term goes to 0, and we can forget about a0. So then we have the integral from 0 to 2 pi of f of x sine of kx, there should also be a dx here, is equal to this guy plus this guy. So let's begin by evaluating this integral. So yes, the integral from 0 to 2 pi of cosine nx times sine kx dx also tends to 0, and we've discussed that before, so this one gets cancelled out. It tends to 0 everywhere. And this integral, the integral from 0 to 2 pi of sine nx sine kx, tends to 0 almost everywhere, except for the case when n is equal to k. So if n is equal to k, then you have the integral from 0 to 2 pi of sine squared nx dx, and where n is some arbitrary integer, and then this is always going to equal pi. So for every other case, for every other n and for every other n that does not equal k, this integral is evaluates to 0. So then the entire sum evaluates to 0 everywhere except for when n is equal to k. So this entire n is equal to 1 to infinity is invalidated, and we only look at the case for n is equal to k. So then we have bn, so bk, because that's only non-zero, and sine of kx. Sine of nx, but this entire integral evaluates to pi, so then we have b sub k times pi. So we've canceled out the first term and the second term, and then we evaluated the third term, and it came to b sub k times pi. So now we have the integral from 0 to 2 pi of f of x times sine of kx dx is equal to b sub k times pi. And we want to isolate b sub k, so then we have b sub k is equal to 1 over pi integral from 0 to 2 pi of f of x sine kx dx. And now what we do, let me erase this. And now what we do is we simply exchange x for k. So, no, my apologies. We exchange n for k, because we have a Fourier series with the sum from n is equal to 1 to infinity, not k is equal to 1 to infinity. So then we are left with b sub n is equal to 1 over pi, integral from 0 to 2 pi, f of x sine kx dx. So this is wonderful. We've evaluated the Fourier series coefficients a0, an, and bn for all n in the last case for all, well, in the last and the first, and so in an and bn, the solutions are valid for all n greater than or equal to 1. And we've evaluated these three coefficients, but keep in mind that we've evaluated these three coefficients only for 2 pi periodic functions. So if you have a function which has period t, which is not equal to 2 pi, then these solutions do not work. So we will be discussing the more generalized solutions in up-and-coming video. Thank you very much.